So in the last lecture, what we did was we sort of proved that infinitesimal angular displacements or d theta can be taken as a vector, and then from there we found a relationship between the velocity and the angular velocity of a rotating object, right? And in that we also proved the assumption with which we started, that this omega or the angular velocity is indeed a vector, right? And can be written down in terms of its component along three orthogonal axes. So we'll try to see where this is useful. Now this relationship dr over dt is equal to omega cross r. Right? So now this is particularly true because if you look at the analysis, then what we did is by writing this, we are saying that r is constant. So basically we are looking at the rotation of this position vector, where the magnitude of position vector is a constant. So the position vector is actually going in a circle, right? And that's where the relationship is true, and that's how we write down the velocity equal to omega cross r. Now, if again we look at the analysis, what we can see is there is nothing special about the position vector. Instead of a position vector, we could have done the exact same analysis for any other vector, right? So this is actually a general relation, which then we can write down that for vector A, so let's say A is a vector, any physical vector, which is now going to be dependent on time, but in a way such that mod of it is constant. So that means we are looking at the rotation of this vector, and if this is the case, then we can write down a general relationship that between the rate of change of the vector and the vector itself by connecting it to the angular speed or angular velocity of rotation about whatever axis it's making the motion. So in general, d over dt is simply equal to omega cross a, and now of course the omega is the axis of omega is perpendicular to the unit vector about a, then this is simply omega a, right? And so this is an important relationship which we can use, and one has to keep in mind always that while applying this thing, what we are saying is the magnitude of A is constant, right? Or in other words, at least in terms of physical systems, what this also means is that the force or the torque which is going to lead to change in R or change in some other quantity, because we know that to change the state of the system, there has to be a force or torque acting on the system, right? So what it says is that the acted force or the acted torque is also going to be then perpendicular to the vector A, and A will then have a particular physical significance. It could be the position vector, it could be the angular momentum, linear momentum, or whatever. Right? Okay. So anyway, so this is the important relationship, and now what I'll do is we'll take an example where we can at least part of the observation can be explained by using this simple relationship, and that example is well, the example is from a bigger problem, right, which is precession of a gyroscope, and I hope you guys have some idea what a gyroscope is, right? For our purpose, as a model system, we can take so let us say this is so for our purpose, what is gyroscope? It's basically a disc, right? A circular disc which is free to rotate about its center of mass, and let's say it's rotating like this, and this is basically then coming out of the plane. So the rotation is in this way, same anti-clockwise rotation about the axis. So it's free to rotate about this point, about this axis, right? And for time I can take this as x, then this will be y, and this will be z, right? So about any origin. So a shaft and a disc. Right? This is a simple model for a gyroscope. Right. So anyway, one sees when one studies motion of such a system in general, one sees various different. The observations are quite unique, and one tries to explain all of those using the rotation dynamics, right? And that's what we are going to do. But we will not consider it in full. We'll just partly we look at one of the particular observations and then try to solve it or try to understand it. And this is something which you have also done. So you can recall now in your PHY 101A lab, right? You do this experiment on gyroscopic precision, right? So it's the same thing. It's the same phenomena which we are going to now analyze in terms of the equation that I wrote down, right? So now let's just first discuss what is the phenomena. So what one sees is, if let's say to begin with, I have this shaft and a disc connected to it which is free to rotate about this shaft, right? I give it a nice spin. So let's say if the disc is spinning with some spin angular velocity, spin angular speed omega s, right? If it's spinning with this thing, and now let us to begin with somehow either on a pivot or by holding in your hand, we make sure that the disc is oriented such that the resultant angular momentum Ls, we'll call it Ls, the spin angular momentum, points in the x direction. Let's say to begin with, right, to the lab space in the x direction. And now, so right now this thing is held like this, right? So there could be a pivot point here. We can make this a pivot point here. This held like this, and right now I'm holding it at this end so that it does not fall down and there is no change in the state. And now, if I let it go from here, right? What one sees is, if the disc is spinning, then it basically starts to rotate rather than falling down, which normally is expected. It starts to rotate, right? So, for example, if I am holding it like this, and the spin angular momentum direction is towards you, then as soon as I leave the other end and simply have it pivoted here, I'll get a sort of force which basically rotates the entire thing in one direction, and of course the direction all will come from the vector nature of angular momentum and the torque applied, right? And so this is observation. One sees that it starts to rotate rather than falling down, it starts to rotate in the plane, right? And now what happens is, so once we say that it starts to rotate, that means this angular momentum Ls, right, is changing. Now, the magnitude of Ls is not changing because there is nothing acting on the spin. The spin is, the disc is, if let's say the bearings are completely frictionless, then the spin is, the disc is still spinning with the same angular speed. However, so the magnitude of angular momentum is not changing, but its direction will change because now it's precise. That's called precision, because now it's moving in that plane circle, right? So direction will change, and now it doesn't matter the magnitude changes or the direction changes. As long as vector angular momentum is changing, there has to be a torque acting on the system, right? So then we have to look for the source of the torque and try to see how we can explain this theme observation. Okay. So now for that, one does have, at least in this case, one does have a source of torque, right? So what happens is there is so if let's say the shaft is more or less massless, then the center of mass of the system is located is coinciding with the center of mass of the disc, right? And then the disc has a mass m, then there is a downward gravitational force mg acting on this. The other end is on the pivot, so there will also be a normal reaction about this. Since the shaft is not falling, the disc is not falling down, the center of mass is not moving in the vertical direction. Now that basically means that the N has to equal to mg, right? So the forces are balanced. However, if the shaft has a length L, then the torque is not zero, right? So the net force can be zero, so that it still has the same vertical position, but the net torque is not zero. And now I can write down for this system torque. So the scalar, so just the magnitude of the torque and direction anyway we can find out. So the torque is then going to be So let's say about the pivot point, this will be mg(L), right? Mg is the weight, L is the distance, this is the torque, and what is the angular momentum? Let's say the initial angular momentum to begin with. This we are calling spin angular momentum Ls, and this is simply the moment of inertia of the disk about its center of mass and the angular speed omega s, right? And now what we are saying is, since this Ls is not changing in magnitude, right? So this Ls is constant, I0 omega is not changing, the disk is not changing. So we can apply now dl over dt magnitude is equal to, now in this case, let us say the velocity which is, or the angular speed which it gets in the horizontal plane is omega. Just to differentiate this from the spin angular speed of the disk, omega and L. So basically omega cross L, and then the magnitude of this, right? But omega will have a direction which is perpendicular to Ls, so this is going to give us simply omega Ls. Okay, so this is fine, and we also know that this is also equal to tau. So this is equal to tau, which is my mg(L), and from here what we can do is we can find out this capital omega, which is the angular speed of precession. So this motion of the gyroscope, so this is my gyroscope under because of this torque we call it precession. So instead of falling down, it starts rotating in the horizontal circle. So omega, and this is then equal to, well, mg(L) over Ls, which is nothing but I0 omega s. Okay, so basically what we can do is, so we know the forces or the torques which are responsible for this kind of motion, and we can get the angular speed in terms of the known parameters now, the mgl torque acting and the initial angular momentum I0 omega s. Of course, again this thing is strictly valid in case where this capital omega is smaller than or much smaller than this omega s. So the disk is spinning much faster, and which is leading to uniform precision in that horizontal plane, right? Another thing that one can see from this one is, if you do that practical, or if you have done that practical in your lab test session, that this capital omega is inversely proportional to the small omega. That means faster the disk spins, slower it will precess, and slower the disk spins, faster it will precess. This is also something that we have seen in case of the toy tops, the spinning top, which is a very good example of gyroscopic motion. So there also one sees that when the top is spinning very fast, it's more or less stable in the vertical along the vertical axis, right? And even if it's precessing, its precessing speed is rather slow. You can see it nicely making a conical circle about the vertical, right, at a particular angle. But as the top starts losing its angular speed, slows down, you see that precision gains more and more speed, and later on of course the motion becomes more and more chaotic. So we don't have to go there. So we can explain these things using this simple relationship, right, which we derived now, which we now know is in general true for any vector, right, whose magnitude is constant and yet it's changing in time. That means, and that is only possible if the vector is actually rotating with certain angular speed omega. Okay. The last point that we can also talk about this example is, it's not necessary that this shaft has to be placed in the horizontal direction, right? In fact, we can place this shaft at any angle. So let's say this is my pivot, so that this becomes my initial Ls, this is the spin direction omega s, and then let us say this is the vertical, this is the horizontal. So now let us say that if this is the angle theta, it doesn't matter what is this angle theta, it could be anything, the value of omega, if I write for this case, will still come out to be this. Simple reason is because now this is mg acting this way. Simple reason is the torque here on this system. So this, if this length is L, then this is L cos theta. So the torque is basically mgl cos theta, right? Also, now this S, so if you consider x and y as our coordinate directions, then Ls can be written down or broken up into two components, Ls cos theta and Ls sin theta along the vertical horizontal direction, because we know that Ls is or L is basically a vector quantity. So this kind of we can take different components of Ls along our chosen coordinate axis, and now Ls sin theta is going to be constant, right? Because pointing in the vertical direction, and the angular speed is well, we find the present speed. So Ls sin theta is a constant. So the only change with time is in Ls cos theta, right? So then when we put it here, will we match it? Then my equation will be dl over dt, right, is basically going to have omega cross Ls, right, which is then Ls cos theta, right, and this is also equal to the mgl cos theta to the torque. So it doesn't matter what is the angle, this angle term will get cancelled out, and effectively we will be back with the same equation for angular speed omega. Okay. So anyway, so this is, it just demonstrates that this angular speed omega of precision is independent of what is the angle. Of course, if theta is vertical, that means the disk is spinning like this, and Ls is in the same direction as omega. Then we know that is there is going to be no precision, because again there is no torque now. Now mg will be nicely balanced by n right here at the center of mass, and there is no torque. If there is no torque, then there is no precision.